split up. Okay, no. For the exercises, we will later split up.
So maybe start from the beginning.
Yeah. Okay, was a bit delayed. So, right. Okay, so welcome everybody to the ChEESE Advanced Training on HPC for Computational Seismology. My name is Christoph Niethammer, and I will guide you today through the event. Here's a short overview of the 3 days which we will have. So we have 4 different codes which we will show you. As said, the presentations will be performed by Zoom, and we will use here breakout rooms for the exercises. So we have the main session in this main room, which is depicted in this blue color for all the sessions which will be in the main room. So this is mainly the introduction as well as the general code presentations. And then we will have later on the exercises in this breakout rooms shown in magenta here. In between, in the lunch break, we will have lightning talks where you presented yourself in a short video. And I would suggest that everybody who did not send a video in just listens to the videos we have already today and then provide one as well, so we can have a short introduction to the people over the next 3 days also. Getting in touch, knowing each other a bit better. So here's a detailed timeline of today's schedule. We start with today's introduction on Zoom now and how to use the cluster for the exercises in general, how to access them, checking that everything is working for you. And then we will directly jump into the 2 main codes, which is ExaHyPE and SeisSol. There will be presentations from our trainers before, and then we will have a break. And after the break, you will go into the introduction of the next 2 codes, SPECFEM3D and Salvus. And after lunch break, then we will have the lightning talks. Depending on how fast we are, we can adjust here the lunch break for you as well. And then afterwards, we start with the first set of exercises on SeisSol. The meeting will end around 16:30, but I guess everybody who has questions has still a chance to stay here and chat with the teachers and lecturers. Good. If there are any questions, you can either type them now directly in the chat in Zoom, or if you are already connected to the Slack channel, then you can also type in the Slack general channel. I will try to keep an eye always on the Slack channel as well. So anytime you have a problem with the system, or let us know, and we try to help and get it fixed as soon as possible. Okay. Good. Then have a short introduction to Zoom and our clusters. So I guess.
Can I just say one quick word before you? So sorry, I'm Lorenzo also from HLRS. I helped you with the registration and with the logging in the cluster, and I hope I could help most of you. And I just wanted to say one quick word before you go ahead with the training. In Zoom, please state your name as name, surname, and institution, because if you use a nickname, then we cannot see who is there, who is not there, and I will have to ask you. So if you can, please use name, surname. And at the end of the training, short before the end of the training, we will ask you to please complete a feedback form. And it is very important for you to get the certificate and for the trainers to improve their training. And I think that's all from me. Yes, the Slack link to join the channel is new, and I just pasted it in the chat. So some of you already asked me for the new link, and I have it. Otherwise, use the one in the chat. Okay, that's from my side. Christoph might proceed.
Okay. Thanks, Lorenzo, for the info, so that we can stay connected. Yeah. So everybody, I guess, is familiar with the not regular Zoom. We use here an additional feature of Zoom, which are the breakout rooms. So for all these who didn't use them before, that's the general overview. Currently, we are all in this main session with all participants, all trainers, where you always join when you come into Zoom. And for the exercise later, we will have additional rooms. They will be activated by Lorenzo in this case as the host. And as soon as they are active, it's possible to join into these rooms, and we will split up the trainers over the rooms, so there are smaller groups. So you have a bit better of chance to get feedback, to ask questions in a smaller group. Beside this, there's also the Slack channel where you can always ask questions, and we try to have an eye on this, and then directly, either answer you in Slack, or you can go out and have a private conversation in a room. How does it work now? General features of Zoom are also like you can give here the instant feedback. We have these breakout rooms I mentioned. You can share your screen in any case you have a problem, or we can share you the screen so that we can show something. You can even grant remote control in case you have a problem, for example, and you have to type commands in the command shell, which we would have to tell, or you would have to copy paste from somewhere. Sometimes it's faster just to hand over remote control for this terminal, and then we can directly operate on your screen. And there's also a button just to ask for help immediately. And we have here in the following a few pictures so that you find yourself around. So if you did not activate the participants list, on the bottom there's this participant icon. If you click there, you will see on the right hand side a long list of all participants and teachers. And there you see also if you are muted or not. So if you are not muted, please mute yourself, as we do also the recordings for the later sessions, and we will provide them to you if you have want to re-listen this on our services. There are also then additional buttons where you can give instant feedback, like when we have a question, you may be able to just click on yes or no, or whatever is available. You can raise your hand, so if you want to tell something, so then we can make a short break, and you can post your question by word, or if you like. Then this breakout feature for this additional rooms for the exercises, as said, this will be activated from our side. And as soon as it's active, you should see this breakout rooms button on the right corner of the screen. If it's not available, sometimes there are 3 dots and you may have to the additional options. So then you will find it there. As soon as you click on this button, you will get a new list with a number of room names, and then you can join one of them by clicking and then pressing join. Then you will be brought out of the main channel into this room, and you can talk there as normal. When you want to go back, there's on the same place like a leave button. When you click on leave, you will be presented with leave this breakout room, and depending on how your GUI looks like, there might be also like a leave the meeting button at the same time. Don't press on this, that's normally in red. Use the blue button and just leave the breakout room, so you end up again in the main room. Don't jump out of the meeting, so then you would have to reconnect, and Lorenzo might have to re-add you from the waiting room. Then, as you know, there's always this screen, green button for sharing the screen. And as soon as you press this, you get a prompt with different windows, which you might share from different applications, or you can share the entire screen, depending on what's best for the moment then. What is important, as soon as you share the screen, don't move the windows around. Otherwise, you have black screens, or you might see something which is behind, depending on your operating system, your settings. So leave the windows then where they are. Then for all these which are in presentation mode, there's on the top then this green and red bar instead of this bottom bar, which you have normally for control. As soon as you go over with the mouse cursor on this, you will be presented the normal normal controls, plus additional remote controls where you can paint on the screen. So if you need to highlight something, you can use colors just to mark stuff and also clear this again later on. Good. Then if you have any questions, there's also an Ask Help button on the lower corner, which you can use, and then we will jump on you and try to answer. Are there questions so far? Okay, I don't see here.
I just might add that each trainer can open and close the breakout room, so I don't have to do it for each session.
Perfect. Good. So I don't see any more questions in the Slack and in the chat here. So let's jump to a short introduction how to use the cluster. For cluster usage, everybody has provided already a SSH key. I hope everybody is familiar with this, as we will do all the exercises on a real HPC system. So you get really first hands-on experience with the codes on a good system, and don't have to do this on your laptops or workstations. To connect there, you need this SSH client, for which you provided already an SSH key file. If there are any problems, let us know in the Slack channel. And in the Slack, there we have even special rooms for this. So either SSH issues or SSH problems, they are called. We will look specially with the specialists which are familiar with all the setups and the logins. Everybody of you should have gotten a login account, which is this SCA 509, and then a participant ID. Remember this participant ID, this might be used in different places later on. For example, for the distribution to the breakout rooms. So just as a short test, I would now give you the chance to test your SSH login. So open a prompt, please, and log into the cluster. And then you can also use the feedback buttons in Zoom and tell me if you are able to log in. I see already a lot of OKs pinging up. So if somebody is not able to log in, give a no. There are thumbs ups. That's also fine. Perfect. 5, 6. Scroll a bit. Okay. Good. I don't see somebody with a no or comment so far. If you encounter any problems in the during the course logging in, use the Slack and post this in the SSH channels. And then Lorenzo or myself will try to help you immediately. Good. Then here, general issues if there's something going wrong now. As said, we use the SSH private keys. If you use or the -i option directly of the SSH command, provide the private key, not the private key, the private key, not the public key here for this option as a name. Or if you have set file permissions on your keys wrong or on the directories, SSH may also complain to log in. And otherwise, there's the SSH channel. Good. So if everybody is logged in, I would do a second test. If your account is working properly, if we gave you the right permissions. So we have prepared a short script to set up your environment. And this is located under this shared ChEESE setup path. And you should just type this in your command line as it is and press enter. So the setup shell script will be executed. And then you should see the below output, which tells you that you have created workspaces. So that's different folders for you where you can store data later on. Yeah, extensions, like you can prolong them if you are working for a longer time on this, but that's maybe not relevant for us. And then it will tell just that it set up subdirectories or links to other directories correctly with 2 OKs. So can you please try this command? And if you see any problem, then also raise your hand. I will check the chat in between, where I see lots of yeses. Okay, I see 1 no. So maybe the person who typed no can write in the Slack channel or in the chat what was the problem. Okay, otherwise we will come to you in the Slack channel, maybe best. Good. If this is now completed correctly, you should see in your home directory, if you type an ls now, a ChEESE directory, or better a link, which points to a shared ChEESE directory with materials, as well as a work directory, which is a link to this special workspace folder in our file system. So you don't have to type every time long paths. And I would recommend that you just change into this working directory at this moment. And all the exercises will now use this working directory later also to run jobs. Don't do this in the home directory, as the output in the home directory will stress the file systems, and yeah, that's not so good for the system now. Good. Are there questions at this point? Working well, working well. If not, then as said, in general, we will record all sessions here in the main room and also in the breakout rooms, and provide them later on for so that you can have a second rehearsal on it if you want. So if you don't like to talk, just type in the chat. Otherwise, you might be in the recording, or tell us when it should be cut out something. Then for jobs on the cluster, I hope also the trainers will teach you later on again. We have reserved resources for every participant. However, the resources are limited, so you are only able to run one simulation or one job at a time. So please, if you encounter problems normally and you want to run a job and it doesn't start, you might be running another one already. So be aware of this. Besides this, as mentioned already, we have these lightning talks. Who didn't know how the lightning talks worked, just listen to the first set of lightning talks we already received, and then try to provide them in the next days, so we get to know each of you.
Yes, Chris, we also have the introduction from Arnau Folch, who is the coordinator of ChEESE.
So I would hand over to Arnaud Foch, who's the project coordinator of ChEESE. And afterwards, I would welcome everybody to have a short group photo via Zoom. So everybody then can enable his video who likes, and we take a picture. Good. Then,
thank you. Yes.
Hope I didn't cut you too much time.
No, it's okay. Thank you, Christoph. And well, good morning, everyone. I think you need to stop sharing because otherwise I cannot take the. Okay, thank you. Okay, so good morning, everyone. My name is Arnaud Folk. I'm the coordinator of the ChEESE, the Center of Excellence for Exascale and Solitaire. And I've been asked to give a very, very short talk to introduce ChEESE to those of you that are not familiar with this project, with the Center of Excellence. ChEESE is one of the already 15 centers of excellence that we have in Europe. And it's a project that started in November 2018. And it's going to end by March next year. This is actually a consortium that it's made of 13 partners from several countries, from seven European countries. And in the consortium, we have supercomputing centers, but we also have institutions that have operational mandates in geophysics, academia, and a couple of companies. The high-level objectives of ChEESE are, first of all, to prepare what we call flagship code. So we are preparing 10 codes for the upcoming pre-exascale and exascale machines that will be deployed soon in Europe. But we also have scientific objectives. We want to use these codes to address what we call exascale computational challenges, that are problems that need of some exascale capacity or capability. And also we want to develop service prototypes, and we do this by means of what we call pilot demonstrators. We are developing and implementing 12 pilot demonstrators that are proofs of concept to enable future services oriented to several aspects of geohazards. And then there is a fourth objective, which is an important objective, which is community building, that aims at integrating around HPC and HPDA all the research institution, academia, industry, and public governance bodies in general. And that includes training, and this is why we are here today. No? So, as I said, we have 10 flagship codes, 4 of them on computational seismology. This course is about these 4 codes, but we have other codes. We have also 2 codes on magnetohydrodynamics, other 2 in volcanology, in physical volcanology, another 2 in tsunamis. And what we do in ChEESE is, okay, we took this code at the beginning and we are doing several optimizations at intra or inter-node levels, thread parallelism, optimization of memory aspects, porting to accelerators of several parts of the code. We have already ported 8 of these codes or parts of them. We also deal with aspects such as load balance, parallel and asynchronous I/O, workflow managers, schedulers, etc. And we use these codes in these 12 pilots. The pilots are, let's say, a different technology readiness level, but we have 8 that are at a high TRL and are already service candidates. And this will be, or I've been testing together with potential end users on several aspects, like ocean computing, hazard assessment, early warning forecast, seismic tomography. And as I said, we also have 4 that are at a lower TRL, that are yet at a more scientific level. No? Regarding training activities, we have been very, very active in these 2 years. We have done lots of courses on several codes, for example, on ExaHyPE, on HPC, for tsunamis. We also have done 4 GPU hackathons in collaboration with NVIDIA, 1 in 2019 and 3 this year. Another course on risk analysis, a joint school with the ASEAN countries, and then 4 PATSI courses, advanced training courses that we did 2 in December 2019 and 2 this year. And that included the first course on computational seismology that was done exactly 1 year ago. This course was actually very, very successful. Many of the people, probably some of you, could not get in. And this was the motivation for repeating this course. And we are having today the second, say, edition of this course. And that's our 5th path course that we're going to have these 3 days. I just want to acknowledge all the organizers, and in particular Jose and Christophe from HLRS and Ros Gregory from BSc, and also all the local organizers from HLRS and the PATSI training centers in general, and of course also all the people that will be training you, all the lecturers from these 4 codes, from SPECFEM, from SeisSol, Salvus, and ExaHyPE. It's a long list of names. If I forgot someone, please excuse me. Just if you want to know more, you can just follow us on LinkedIn, on Twitter, or through the internet. So that's it from my side. I just want to wish you a very successful training. You are in very good hands. You have an excellent expert, a team of experts, and that's it. Enjoy the course and all the best. Thank you. That's it from my side, Christoph.
Okay. So, thank you, Arno. Yeah, just making a bit of break for cutting the videos later on. Yeah, so I would say then we can start with the introduction to ExaHyPE if there are no questions.
Sorry, Christoph.
Yeah, do the photo before.
Yeah.
Do the photo. I will just check the Slack channel if there are any questions in a second. No, and the chat is also no questions. Okay, good. Then, yeah, whoever wants to, be on a group photo, say just enable your cameras, and then.
So for your information, this group photo will be used on the ChEESE social media channels and possibly on the website. So this will be a public photo. So if you want to take part, please turn on your camera.
And please smile.
Yeah.
Even though it's early.
Yeah, we can all say ChEESE. That's just telling the, let me just check that I can. Rosa, will you also take a few screenshots then? Yeah, so I'm taking them now, but okay. I need to take scrolling through a bit of pictures and then smile. Okay.
It's really great to see everyone though.
Yeah. I hope we can do this in person soon again. So that's a many screens. Okay, see lots of happy faces. It's nice, and I'm looking forward to the lightning talks that we also know what everybody is interested in. And okay, I took a few pictures. Thanks a lot, and yeah, I would then hand over to our first session. And that's my screen. So we will start now with ExaHyPE. Okay. And this is then going on until 10:30 around.
No, it's 30 minutes and then we have the SeisSol part.
Yeah. Good. Then yeah.
I think then I will just start. Or...
Yes, you can start. Screen is free. So.
Can you also see my screen now?
Coming up. Yes, perfect.
Okay. I will close this. Then I think you don't have the black square. So I will talk about seismic simulations using the ExaHyPE engine. First, let me introduce myself briefly. I'm Anne Reinardt. I'm now at Durham University. And I was at TUM in the group of Michael Bader until quite recently, which is why I'm involved in this workshop in the first place. Now I need to. No, I can't change my slides for some reason. Okay. So first, what is the ExaHyPE project? So the ExaHyPE project is something that has been running on for a long time now. It was originally an EU Horizon 2020 project. And it was, in the call towards exascale high performance computing. In particular, it was using some new mathematical and algorithmic approaches, which is the ADA-DG approach, which I'll talk about in more detail. And then ExaHyPE has received follow-up funding, among others, through ChEESE, which has already been introduced, so I won't do that. Here are some of the people that have been involved with ExaHyPE. There's a lot more, but these are the ones that are involved in this workshop. So the PI at TUM is Michael Bada. You've got the instructors for this workshop. Leonard Rannabauer will be just hopping around, and the three main instructors are Philipp Samfas, Lukas Krenz, and Mario Wille. So they'll be taking care of you, hopefully. And now let's get back to what is ExaHyPE. So ExaHyPE's goal was originally to construct a PDE engine where engine was intended to mean a game engine. So that means it was intended to give people the parts that they needed in order to very quickly put together a working code. So it should enable medium-sized interdisciplinary research teams to realize extreme scale simulations quickly. And for this, it prescribes you the numerics that you have to use. So one of the things that was decided upon is that a game engine would also provide you certain things, and you can't change them. So in this case, you have to solve on Cartesian grids, and you have to solve using high order ADA-DG schemes with subcell limiting. Feel free to interrupt with questions. I can't keep an eye on the chat, but if you say something, I'm happy to take questions in the middle. The primary focus has always been on two different application areas. So the first one, astrophysics, I will not talk about today. The second one was seismology, and I will talk about that today in more detail. So here's the very general form of the first order hyperbolic PDEs that ExaHyPE can solve. So this was tried to keep as general as possible, so it can solve anything that's a first order hyperbolic PDE. And so we have a time derivative here. So Q is our state vector. That's the vector of unknowns that we want to solve for. We have a derivative in time over that. We may multiply it with some material matrix if we want. Then we have our flux term. So this is a gradient of a flux term of that state vector. Then we can additionally have non-conservative fluxes given here by these BI. And on the right-hand side, we can have quite general source terms and also point sources. So this is the general setup of the engine. So the puzzle pieces are supposed to tell you that this is a modular code that you can stick together, which isn't entirely true. You are kind of stuck with the high order ADA-DG. There's no other real alternative. You can, to some extent, insert finite volumes here if you like. So this is the first component. So we want to have a high polynomial order so that our workload per cell is very high. And so we've chosen a DG scheme where each cell is basically computed independently. And we've chosen ADER time stepping. ADER stands for arbitrary derivative. And that is supposed to tell us that we can get an arbitrary derivative in time when we're doing ADER time stepping. So this is essentially one of the alternative approaches to something like a Runge-Kutta scheme. And we've chosen ADER because it's a simple predictor corrector scheme. So there's no stages like in Runge-Kutta where you'd have to compute through multiple stages. There's just two, predicting and correcting. The next component is the finite volume limiting. So in DG schemes, you often get something which is referred to as Gibbs phenomenon, where at places of discontinuity, you get spurious oscillations that shouldn't be there. And there's a lot of different approaches around for how to solve this issue. We've chosen finite volume limiting. The basic idea is really simple. In those cells where we find these spurious oscillations, we just go back and we compute with a finite volume scheme which doesn't have this issue. And we do this on more cells than the original DG scheme because the finite volume will be low order, and so the accuracy of it would be lower. And so we subdivide that cell into more subcells, which is why we call it subcell limiting. And then we compute a finite volume solution which doesn't have the spurious oscillations. And then there's some more code-based considerations. So in order to create hardware-aware code, we use code generation, and this will optimize your code for the particular architecture that you're using. And then the last component is, of course, the grid. And ExaHyPE always builds on grids of cubes, but it does have tree-structured AMR, so you can refine in certain regions and not in others. And here's basically the engine architecture and application interface. So ExaHyPE always tried to keep a separation of concerns, which means that for the user, the only things you need to worry about are the orange parts in this graphic. And everything else has been separated out from that, and you don't need to worry about it. So the ExaHyPE core consists of all the actual solvers and the algorithms, the time stepping, also Piano, which is the grid framework, and our optimization library, libxSMM. And so as a user, all you need to write is your PDE term. So that's the stuff that's in turquoise here. That's what you write as a user. And the only thing you interact with is the actual user solver, which is generated by the ExaHyPE toolkit here in orange. So in a bit more detail, as a user, you provide C or Fortran code for the fluxes and the source terms and so on that we saw in the slide giving the general form of the hyperbolic PDE. And then the toolkit will generate you kernels which are tailored both to your particular PDE, so the number of variables, for example, and also to your hardware. And then everything underneath that is Piano framework or the ExaHyPE core. And as a user, you don't need to worry about this, but this is, of course, where all the actual algorithms are implemented. And since we've built up quite a general engine, you can implement highly different PDE systems in it. So here's a list of just some of the equations that people have implemented in ExaHyPE. And I've bolded the ones that I will talk about today. So the Euler equations were sort of the first model problem that was started with. I will today talk a little bit about tsunamis, which is some quite recent work. And I will also talk about curvilinear meshes for the elastic wave equation, diffuse interface approach, perfectly matching layers, and the Godunov-Peshkov-Rumensky model. Everything else, like compressible Navier-Stokes, which is technically actually not hyperbolic, but can still be solved in the ExaHyPE engine, I will not talk about. Okay, so let's start with curvilinear meshes. So this is work by Kenneth Duro and Leonard Rannabauer. And essentially what happens here is we're just solving the elastic wave equation. And we now need some way to get the topography in. And as you saw on the previous slides, we're just working on cubes. And so somehow we need to resolve topography. And so with the curvilinear meshes, the approach is that we map each Cartesian mesh cell into a boundary fitting curvilinear mesh. This requires initial mesh generation, which has been automated. And then your PDE, the flux and the source terms are just transformed. In this case, the eigenvalues and the time step size depend on the norm of the transformation. So that means that if you have a very steep topography, your time step size will become very small, which in turn means that your algorithm becomes much more expensive. If you have a very smooth topography, then the time step size can be quite high, and it becomes less expensive. So we have one alternative approach, and this is the diffuse interface approach, based on a paper by Tavelli and Dumza. And in this, we essentially just keep the cube, and then we add an additional parameter to our equation, which identifies which parts are solid medium and which parts are not. So if you look at the picture on the right, then some of these cells are completely empty and other ones have topography in them. And this parameter alpha is just telling you where is the solid medium. So it will be 1 like completely in the interior, it will be 0 completely out of it, and in the sort of interface area, you will have a diffuse zone, which is why it's called a diffuse interface, where the value is somewhere between 0 and 1. This approach completely avoids the problem of mesh generation, but it does come with a trade-off, because now at these boundaries where alpha is between 0 and 1, the fluxes are no longer linear. And that, of course, causes its own problems, and is also quite expensive to solve that in a different way. But as an advantage, the eigenvalues and the time step size are both now independent from the topography, which means the steepness of your topography doesn't have any more effect on the time step size. It also allows to insert moving meshes quite easily. And now let's look at some of the things people have actually done with these two methods. So the first one is looking at scattering effects in the alpine region. So here the goal was to track topographic effects on wave scattering. And to do that, the topography was filtered with different cutoff frequencies. So you can see 3 different examples here, where this one is quite smoothed out, and then you've added a few more frequencies, and this is the most, the least filtered of the ones that are on this picture. And this was then used to conclude on the frequency content. So you can see for, what is this, 6 different frequencies here, the effect on the velocity, for example, and you do get additional waves here that weren't there before. The next thing is the perfectly matched layers. So quite often, if you're looking at a seismic application, you get in reflections from your boundary. So if you make your domain not big enough, then some waves will bounce back in, which is obviously not physical behavior, and it's something that you want to avoid. And you want to remove these. And the perfectly matched layers do this. It requires quite a complex mathematical calculation, which in this case was again done by Kenneth Thoreau and Leonard Rannabauer. But the effects are quite nice. So you can see on these pictures here in red in red with the perfectly matched layers and in green without. So this one should be 0. And with the perfectly matched layers, we see this, and without them, we do see these spurious modes that we shouldn't be seeing. In ExaHyPE, this is quite easy to add in some sense, because the engine interface makes it possible to quickly add in. The next thing to look at is multi-physics dynamic rupture, where I've made a typo on the slides here. That should be multi-physics, of course. And in this case, instead of taking simple initial conditions, what we want to do is just prescribe something on a fault as your initial condition. And so in this picture here, the fault is shown. And this one is a quite common benchmark example that's also calculated like this. And then the rupture can be incorporated. Next, we've got the Godunov-Peshkov-Rumensky model. So this is actually a completely new model. And for this part of the project, the goal was to model continuous damage and freely evolving dynamic rupture. So the Godunov-Peshkov-Rumensky formulation was completely new at this point, and is also going back to Michael Dumser. And we can now use this in order to see secondary cracks here and here. Okay, and so the last thing I wanted to talk about as an example is some more recent work where we've connected ExaHyPE to an uncertainty quantification library called MOOC. And MOOC is a C++ toolbox for uncertainty quantification, which gives you a lot of methods out of the box. And we've been quite happy that we've managed to connect this with ExaHyPE in order to be able to use ExaHyPE not just for forward problems, but also to solve Bayesian inverse problems. So in a forward problem, if you had, even if you wanted to quantify the uncertainty with a Monte Carlo-like method, you could compute individual samples completely in parallel. So that's this row here. You're just throwing the dice, you're computing a sample, and then you're maybe taking the expectation value or whatever you're interested in as a quantity to get out of this. While for the inverse problems, each sample depends on the previous models, so it's not as trivial to parallelize. So essentially in a Markov chain, what you do is you start out with some throw of the dice, some random sample, and then you check how likely the sample is, and then you either reject or accept this proposal, which will then show you the most likely regions for your parameters. Okay, I think I will skip this more technical slide on the idea of multi-level and just say that as we saw with the frequency domain previously, where you could filter the topography, it makes a lot of sense with these algorithms to look at different levels of discretization, because the very cheap ones can then be computed a lot of, and you can then get away with computing very few of the extremely expensive models. And let me just show you the hierarchy of the grids, then this makes more sense. So what we looked at in particular were the shallow water equations. So we looked at the Tohoku tsunami, and we resolved the topography in 3 different levels, essentially. And the first one doesn't have any topography at all, it's just completely depth averaged. And this model takes just under seconds, I think, even. So it's really cheap. We can do lots and lots of this, but of course, the output of it is not very accurate. Then we've got a smoothed out topography. Again, this is just filtered, where we can see quite a lot more. And then we've got the full topography. And then we fed this into a multi-level Markov chain Monte Carlo algorithm in order to try to infer from data at certain buoys what the most likely origin of the tsunami is, which in this tsunami is actually known, so we could double check whether we were correct as well. Here are the results. So for the level 0, each of these dots represents an entire sample, so that's one full PDE solve for each and every single one of these dots, although these ones were very cheap. The little red X marks where the actual location is expected to be. And so this is not going into completely the correct area, but you can see that it's also not completely off. And so this helps inform the samples that we propose for level 1, so that we need to do fewer of those. And those are getting already very close to the true solution, or what we've used as the true solution. And then the last one, which is our most fine grid and the most expensive to compute, we've done only very few samples, but they're already clustered exactly around where we expect it to be. So that's essentially what these are doing. They're more and more restricting the area in which we search with very cheap models, so that we only have to do very few of the very expensive ones. And this is a paper that was recently accepted as supercomputing, so that will be coming out soon. Okay, let me briefly talk about scaling. How much time do I have? Not a lot. Okay. So this is scaling on SuperMOOC, and it's back to comparing the diffuse interface approach and the curvilinear method. And what we can see here is that for the diffuse interface method, we get considerably better scaling. It reaches about 1 giga-DOF per second on 731 nodes. So this is about 14 million elements. And for the curvilinear method, we don't see very good scaling. This is because this is just a linear problem. And so the amount of computational effort per cell is now really low, and it's very difficult to get scaling for that. But what you do have to see is that each degree of freedom is much cheaper to compute with a curvilinear method. So it actually is still computing a lot of degrees of freedom per second, even if it looks like the parallel performance has kind of degraded completely. So there's a lot of challenges that this brings for the engine development. There's a lot of functionality to be tested. There's a lot of different targets for parallelization and optimization, because we have to look at linear problems and nonlinear problems. And sometimes people add new problems, which might then not scale the way that you expect them to. Additionally, an equal number of cells is not an equal execution time, so that's difficult. And thus in ExaHyPE, it uses a task-based paradigm. And these tasks are built on a producer-consumer pattern, which I don't actually want to talk about so much. So the relevant bits here are the communication avoiding traversal scheme to minimize data transfer, and the code generation, of course, which really enables us to try to achieve these multiple targets for parallelization and optimization. If without the code generation, we wouldn't have a chance to do this. Okay, and finally, where can you actually get the engine? So you can find documentation and so on exahype.org. There's also a webpage, which I think is still up, which contains statistics, galleries, and publications, which was from the original ExaHyPE project, but which may be taken down at some point. And I'll close with the guidebook, and then I'm happy to take any questions.
Yeah, I wonder, thank you, Anne, for your presentation. Could you elaborate a little bit more about Monte Carlo chain approach that you used?
So basically we use the pretty simple Metropolis-Hastings Markov chain Monte Carlo method. Just keeping to the basics on this one. Or maybe I'm not getting your question. Would you like me to explain the method more, or?
No, I just wonder if you use an advanced Monte Carlo.
No. So far we haven't. Although the reason why we chose to create a MOOC interface instead of just implementing our own was so that we get access to the more complex methods that have been implemented in that. But so far we've just used the most basic.
Thank you.
So, are there more questions? I don't see something in the Slack so far. No questions in the chat as well.
everybody's thinking about which equation they will implement in the training, I think. Astrophysics, tsunami, earthquakes.
I have a question. So you showed, I think in one slide, you have 0, level 1, level 2 model. And I was just wondering if you stack a lot of level 0 model, would you improve the accuracy instead of doing more expensive level 2 model? Thanks.
I hope I'm understanding the question correctly. So I guess the question is kind of how many level 0 models do you have to take versus the more expensive levels?
Yes. So
yes.
When you do a lot of cheap models and then you stack them together, would you improve accuracy?
No, so there's a limit to what the very cheap model in our case doesn't even resolve any topography at all. So there's a lot of features of the true solution that it will never be able to capture, no matter how many samples you compute. So at some point the payoff also drops off, and adding more samples on the low levels will not give you any additional information anymore. There is actually, for problems which are not hyperbolic, a lot of rules for how to choose the number of samples on each level. And if you're looking at, for example, an elliptic problem, you can prove how many samples at each level you should be taking to get an optimal performance of the algorithm. For hyperbolic PDEs, there's sadly, as far as I know, no such result yet. So we've just used some heuristics where if we see that the low level ones are stopping to pay off, then we add more high level ones instead.
Thanks.
Okay, if there are no more questions for this part, then let's continue with the second code, SeisSol.
Yes, thanks. That will be me. So I share my screen.
Yeah.
Okay. Good. So this is a short introduction into the second code that this training will be based upon. That is SeisSol. So that is HPC code for computational seismology and earthquake physics. And we will focus a little bit in this training on the earthquake physics part, because that's kind of, we're trying to give you an overview about the specifics that each of these methods have, and what specific problems you can solve with each of these codes, even though there's some of them, like the wave propagation, that probably all of them can do equally well. And first, I want to remind you that in preparation for this afternoon, please visit our training GitHub website. Please also check that you have Docker installed and that you have ParaView installed. And once you did all these steps, you can try and run, or you can try and pull also our training image that we will need this afternoon. So that will be the first training. So please try, and if you haven't done so, do this now, so you're ready at 1:30 when we start getting our hands on the code. Okay, the SeisSol team here. We have some dense collaboration between the LMU Munich and the Technical University in Munich, and put recent team members on the slide. And the trainers for you today will be Carsten, Thomas, Bo, Aniko, and myself. And of course, we also, I'm very grateful for funding and projects that have supported the development of the code. And in introduction slide here, I show you a global seismic wave propagation simulation using unstructured tetrahedral elements. So that is already one of the specifics of the SeisSol code, that we're using not hexaeders, but unstructured tet meshes. And the code started off as a computational seismology tool. And computational seismology has been really a pioneering field for high-performance computing over many decades. That has been a fundamental benchmark or a fundamental application benefiting from developments in HPC and also challenging HPC developments to be usable for our field. And why is that? It's because seismology is typically data-rich and can be treated in simple cases as a linear hyperbolic PTE system. And that is the wave equation is something that also every computer scientist is familiar with. And the key activities in computational seismology typically consist of calculation of synthetic seismograms, nowadays in 3D Earth, and solving seismic inverse problems. And we do that by splitting up our solution in the time domain into a space-dependent seismic wave field, and you're solving that by splitting up your model into several chunks, and which each of these chunks can be distributed over a cluster or many core machine using domain decomposition. And there's some ongoing challenges, specifically that we often don't know 3D Earth structure to create as great detail as we would like to know it, especially if you're interested in the high frequency content of the wave field, computational efficiency, complexity of the geological subsurface, and the need for open community solutions as, for example, SPECFEM, ExaHyPE or SeisSol, and many other codes that are developed by the community. And you could argue, though, that the forward problem for seismic wave propagation is solved, and the challenges are more on the efficiency and on the geophysical side of things. And in computational earthquake seismology, the situation is a little bit different. In earthquake seismology and also in earthquake engineering, we often require multi-scale and multi-physics capabilities from our solvers. So here's an example from SeisSol, where we have a Landers earthquake simulation where you see these faults that are all rupturing following nonlinear frictional failure law, and that is nonlinear coupled to seismic wave propagation. And here's the speed code, an engineering seismology simulation of the seismic response of the Canterbury, New Zealand building structure here to the earthquake strong ground motions and soil city interactions. So these are multi-physics capabilities that are required. And we know that recent well-recorded earthquakes and also laboratory experiments that look into earthquake physics reveal really a striking variability of what happens at these kind of sources. For example, earthquakes can propagate as pulses or as cracks. We can have super shear rupture propagation. We can have rupture cascading or slip reactivation of the same patch on the fault during a single event. And if we are trying to understand or incorporate this kind of complexity, we are looking into physics-based source description. So not kinematic or prescribed source behavior, but we are solving for the spontaneous earthquake propagation. And the problem is formulated as a nonlinear interaction of frictional failure along geological fault structures and seismic wave propagation. And then we treat earthquakes as frictional shear failure. Traditionally, we don't allow for opening, also dilatation, with all shear failure of brittle solids under compression along pre-existing weak interfaces. And computational earthquake seismology often bootstraps on methods that are stemming from classical wave propagation, computational seismology. We have to keep in mind that many of them were not originally developed to account for large deformation and large stress discontinuities across these faults. Here's a simple sketch of how a rupture dynamic simulation problem would look like. So we have a fault surface, and as I said, the earthquake dynamics are not predetermined, but they're an outcome of the simulation and evolve as a consequence of the initial condition in terms of loading and strength of the fault, and the way the fault yields and slides, which is controlled by the assigned friction law, which is relating the shear and the normal traction on this frictional interface. So the earthquake dynamic rupture problem is then treated as interface condition in terms of contact and friction. As I said, we are not allowing opening. These two matching fault surfaces, they stay in unilateral contact, and slip, so the displacement across this fault is described as a displacement discontinuity, and much complexity lives in the definition of friction and fault geometry, intersections, and of course our geological model. So that's often been implemented by splitting the fault interface. You see traction tractional slit nodes implementations, often in finite difference codes and finite element codes. So that means we're just doubling the interface and splitting the nodes and then solving the rupture problem across these double nodes. And we don't do that. I'll come to that in a second. And another important point is that if we are including these interface conditions, we often see spurious oscillations being generated, which then have to be damped. And the traditional approach is to do this by adding a thin layer of damping cells around this fault structure. So that could be elements that have strong viscoelasticity, which is not physical, but it's a purely numerical filter to deal with the spurious artificial oscillations. So this is a picture or a summary of our general workflow. If we're doing this kind of models in 3D and on the scale of actual large earthquakes. And we do that to be able to directly integrate a lot of data sets, community data sets or observational data sets, and also to interpret and validate the model with a full range of observations. So for example, we can take high resolution topography or bathymetry, images or models of the subsurface structure. We combine it with friction loss that is stemming from high speed rotary shear experiments, with some, for example, statistical distribution of asperities along these faults. We're including that in SeisSol in our case, and we're generating synthetic seismograms and synthetic geodetic time series, ground deformation that can be, for example, then coupled to tsunami simulations, and of course, everything that happens on our faults. So here, the video that's playing is observationally constrained dynamic rupture scenario of the 2016 Kaikoura New Zealand earthquake. And as you can see, there's a lot of complexity of how the earthquake rupture breaks through this cascading set of faults here. There are also challenges, and there's a really nice white paper that I can recommend I will share the slides later in the Slack channel, and you can click on this link and have a look on this community white paper. And it was prepared in 2019, summarizing some of these advances and challenges, and that's also where I took this plot from. And those include that earthquake source processes are very ill-constrained. We don't have in situ measurements mostly, and highly nonlinear, different to computational seismology problems in their simple form. We have to decide which physical processes are dominant and relevant at a given space-time scale and in real earthquakes, and can we justify to include them in our model. And we are interested in figuring out how to assimilate this knowledge that we have on different scales from field observations to the laboratory in a suitable manner to exploit modern software and hardware. And with this, I mean numerical discretizations, which equations we're solving, energy concerns for high performance computing, and how to use upcoming exascale architectures. So now about SeisSol. So SeisSol is using the ADA-DG method. So we already heard about this. So it's a discontinuous Galerkin numerical discretization in space, and the time integration is called ADA, so arbitrary high order derivative. And this method by design permits representing complex geometries. So using tetrahedral unstructured meshes. So here's an example of how this looks like for meshing or modeling wave propagation at the Mount Merapi volcano. We can account for heterogeneous media, and we have a lot of rheologies implemented and also optimized in SeisSol, from viscoelastic attenuation to viscoplasticity for off-fault damage during earthquakes, anisotropy, and poroelasticity. And we can also have a natural implementation of multiphysics, which we are implementing here by changing the internal flux term. So the numerical flux, which is used to communicate information from element to element, can be adapted to, in our case, solve for frictional failure during dynamic rupture. And here at the bottom, I list a couple of other elastodynamic wave propagation solvers or applications from other groups that are also using discontinuous Galerkin, and also some from our group. And I have a little checklist here of why you could argue for these choices that we do in our code. So why would we be interested in using discontinuous Galerkin? This comes with very low numerical dispersion, and that's important if you're propagating over many wavelengths. For example, you can imagine trapped waves in an equational wedge during a subduction earthquake that are being bounced around, or if you're interested in trap waves and fault zones. We only have to have minor changes for implementing this multiphysics aspects like dynamic rupture. It's very suitable for really intersecting and branching faults. So here's an example of a map view of this Landers earthquake simulation, including off-fault damage. By ADER, it gives us equivalent high order accuracy as in space, potentially using only a single explicit time integration step, which can be cheap if correctly implemented. TETs I already talked about, very easy to fit tetraeders into complex geometrical models. We also have a special choice of the basis functions and the flux, but I can talk about that more maybe if you have questions about this. In general, it's software that allows for rapid setup of models with realistic non-planar intersecting fault systems, or in general complex geometry, while exploiting the accuracy of a high-order numerical method. And the extra flops that we need for solving a discontinuous Galerkin problem, also storage and time to solution, can be optimized using modern HPC techniques. And I'll talk about this a little bit. But first of all, I have a slide about what is the cost of all of this and why is optimization worthwhile to do. And I have here an example. This is one of the most expensive simulations I think that we have currently in our group. So just imagine you want to model 2 linked earthquakes. So for example, the 2018 Ridgecrest, California earthquake sequence. And each of these scenarios should be running for 100 seconds. You want to have 3D subsurface structure, topography, viscoelastic attenuation. You're interested in off-fault damage. And you want to have everything that happens on the fault based to strongly velocity weakening friction and resolve the wave field up to 5 Hertz. So that could cost you in terms of computing, for example, around 170,000 CPU hours for this high resolution scenario. And that would translate into, if you're thinking that energy charge would be 10 cents per kilowatt hour, $320. Or if you're using a cloud service, if you imagine using a cloud service, that would be $6,500. But in terms of energy and in terms of carbon, you can see that this is an oil equivalent of 2 barrels. And in terms of carbon, that would be equivalent to flying from London to Los Angeles. And these numbers are specific for a certain machine. If you would be interested, or if you would be using a more energy efficient machine, the carbon and energy cost would scale accordingly. So it's worthwhile to optimize these problems. And another issue that was already mentioned in Anna's talk is the grand challenge of meshing. So there's currently 2 community standards. Community standard 1 is hexahedral meshing. So SPECFEM is using that approach, and there we can use common tools for doing this also complicated hexahedral meshes, for example, trellis. But there is some limitations for complex geometries, but it's cheaper than the second community standard, which is unstructured TET meshes, which allows for automatized meshing and more easy adaptation to complex geometries. However, we can have numerical challenges by so-called sliver elements that are really badly shaped and causing numerical issues, then also making your simulation expensive or even leading to numerical instability. And the common tools that can be used here and that we will use in the training is Gmesh, which is an open source meshing tool. And in our group, we also use SimModeler, which is free for academic usage. And there's some more information about this modeling tools, meshing tools on this slide. The mesh is provided already in a parallel data format in SeisSol, so the code does the internal partitioning, so you don't have to partition the mesh as a pre-processing step to do a simulation. And Anna talked about this, but I have this also here as an extra slide, emerging other ideas as to the fused interface and the curvilinear mesh approaches to overcome this grand challenge of meshing. A couple of examples where we are rising to this modeling challenges. So this is a dynamic rupture and wave propagation simulation of the 2004 Sumatra earthquake. And these extreme scales of subduction zone earthquakes require numerical methods that handle geometric complexity and highly varying element sizes. And we also have to account, for example, for almost, I think, more than 5 minutes of earthquake rupture here, and wave propagation over a large area. And also we're here interested in resolving the seafloor displacement over a quite large area to be linked to a tsunami model, and to better understand the interaction of the earthquake and the large tsunami in 2004. So the parallel automatic mesh generation workflow for tetrahedral meshes that we have for tested on these kind of models, for example, is working for up to 1 billion of elements. And we're also using local time stepping. And there will be one part of the exercise explaining that in more detail to mitigate sliver elements, so single elements or few elements that are much more costly than other ones. And while a hero run, so a simulation that took a full supercomputer, was running for 14 hours on SuperMOOC 2 in 2017. So that was this SC paper here. Now a typical high order simulation runs for around 5.5 hours on 16 nodes. So it's around 4,000 CPU hours. If you're interested in running these kind of simulations for geophysical applications. And that is enabled by end-to-end computational optimization. And I have a couple of slides later on where I explain this more. The other example I want to show you, since this is your third training example this afternoon, is a rapid physics-based model of the 2018 Palu Sulawesi event, so the earthquake, and was also then linked to a tsunami simulation. And in this model, we were trying to rapidly build an observationally constrained 3D dynamic rupture earthquake scenario from very sparse data. So we've been constructing a fault system, and that's been published in Thomas Ulrich's paper in Pure and Applied Geophysics. So the fault system is constructed from Sentinel-2 and SAR data and regional seismicity. The initial loading and the strength of this fault system can be determined based on the world stress map, and then accounting for transtensional stress regime and high fluid pressure. And then we've been looking into mechanic viability of earthquake rupturing through these 3 segments, and can constrain the dynamics by teleseismic waveforms and moment rate release, and came up with an earthquake scenario that you will be running in a coarser resolution this afternoon. And we found that this earthquake-induced movements of the super shear earthquake propagating underneath Palu Bay may itself play a critical role in generating the tsunami. So this is the linked tsunami simulation here. And I want to also highlight work by Lucas Krenz, which is also a supercomputing paper this year, where we've been working on running fully coupled earthquake tsunami simulation. So not linking an earthquake simulation to a tsunami model, but doing all of this within SeisSol. And the idea is that we have our elastic earth where seismic waves propagate. We have our fault where we're solving for dynamic rupture. And this is linked to acoustic wave propagation in an ocean layer. So what you see here is a mesh of this ocean layer, and also in gravity wave propagation and the water surface. And that is implemented via free surface tracking of a linearized free surface boundary condition that has been shown to work in 2D by the group of Eric Dunham and Stanford. And the simulation that we've been running for the supercomputing conference and that you've been seen playing here was a mesh of 518 million elements, so 260 billion degrees of freedom, and that scaled very, very nicely. Also, for example, on Frontera in the US, and also on SuperMOOC and Mati and Shaheen in Saudi Arabia. So, and with this kind of capability, we can use SeisSol to solve the elastic wave equation coupled to nonlinear frictional sliding on this fault system, acoustic wave equation, and gravity wave approximation as a free surface boundary condition. And we, in this kind of model, what I just showed you, we're accounting for all of these complex geometries, and we solve in the acoustic layer, for sure 15 hertz everywhere, but we're also measuring close to the fault up to 30 hertz acoustic wave propagation. Okay, and I think I'm close to finish. So these are the training examples that we will go through this afternoon. So the first one will be a kinematic finite source model and wave propagation of the Northridge earthquake with attenuation and topography. The second one is a community benchmark for dipping normal fault with off-fault plasticity and dynamic rupture earthquake description. And the third one, as I just said, will be the Palu Sulawesi strike slip super shear earthquake. So in summary, there's a couple of points here that we will also go through this afternoon in detail, but maybe I can end with this again. So after you installed all of these things that I had on the first slide, this is how you can then run Docker, use a link to our image, or you can just run the start script. And after some time, you will see a link. You can click on that link, use the navigation bar to open the exercise, and then you will have in your browser a GUI where you can navigate between all of these different setups. And maybe I stop here, but if you have questions, I have also more slides I can show you, especially about the HPC optimization. So please ask me, feel free to ask me.
Yeah, thank you very much. There's already one question in the chat from Eduardo. About file formats.
Yes, I was wondering about the meshing challenge and if it's possible to have it as a model. Yeah, maybe it could be a nonsense question, but could you have it a meshless simulation or?
That's a good question. You were thinking about like a particle and cell approach or something like this? So far,
yes, something like that. You don't require mesh, but because as you stated, right, it's quite challenging to generate the mesh, even though it's not as good as you want.
Yeah, I'm not aware of that having been tried. Because we're still solving the seismic wave equation, so it's still a hyperbolic PTE that we're solving. And I think what the community thinks at the moment is probably the most interesting is these new ideas of diffuse interfaces and curvilinear transformations that would also mitigate that challenge. But in SeisSol, at the moment it's a traditional approach in that sense that we have our geometrical setup and we are generating a mesh and then we're running the simulation.
Okay, yeah, cheers. Also, the porting that you use, I guess, GPUs. No? You port it to GPUs in order to have this high performance. So this performance that you achieve.
No. It's so the SC paper that is a purely CPU based optimization, but the Ravil student at TOM, he's currently working on the GPU port. So that is a part of ChEESE. That's something that has been, the GPU port of SeisSol is part of the ChEESE task. So yeah, that is in progress at the moment. But the numbers I showed, they were all CPU based.
So it's just MPI, pure MPI.
It's a hybrid MPI OpenMP parallelization. Wait, I can bring up these slides to explain it. 1 second. Okay. Should share screen. So this is a bit of the history and also gives them the references where these optimizations are explained. So they're mostly really led by the Technical University in Munich. And so what we started off with was SeisSol as a geophysics code, so Fortran 90, MPI parallelized, and we had ASCII-based serial input and output. And then in a for the first optimization step, and that was this Landers scenario in 2014 in a SC paper. What was done is that we switched to hybrid MPI and OpenMP parallelization, introduce parallel I/O. So we have we are using HDF5 also for the mesh initialization. We tried at that point some offload scheme for using heterogeneous HPC systems. And the most important is we have this assembler level DG kernels. And all of this led to reaching the petaflop scale in terms of performance, and also 90% parallel efficiency, 45 peak performance. And for users, you would be able to run like much faster and bigger problems. And this is just an illustration of what assembler level DG kernels mean. So there is a code generator which automatically detects and exploits sparse block patterns, and introduces this hardware-specific unrolling and vectorization of all the element operations. So basically taking over the job of the compiler in a customized way. And that is what we're still using, and what has to be adjusted if you, for example, porting to GPU architecture. And then in the next step, and that was this, which allowed us to really reach like the megatrust earthquake scale, or as you can see, the billion degrees of freedom are not that much increase between these two SC papers, but the time steps increased a lot. And this is because this simulation is using local time stepping in a cluster form. And the code generator has been extended here, for example, to also allow us to use attenuation and other more complex PDEs than linear elastodynamic wave propagation. And we're also using, there's a lot of work that has been done into input and output optimization. So there's a geoinformation server, we have asynchronous input and output, and there's also an overlap of computation and communication. And that was a speed up of factor 14 here in that sense. And now what we did for SC21 was basically using the same approaches, but increasing or also porting to like the acoustic in a tsunami problem in the same setup. But that was still an CPU optimization. And what's nice, and that's something that I'm asked sometimes, is what is nice about this this performance optimization for large machines is that it tickles down also to smaller setups that you will be running on your laptops, right? Because you're still the same kind of cores or nodes that you have in your laptop, or even that you have in your phone, are also about building up these large clusters. So it's really worthwhile to take the challenge of this run efficiently on these large machines, because it's also really beneficial if you're interested in smaller simulations. Yeah. I think I'm out of time. But I saw there was a question about
one short question from Gisela Fernandez. If I think that's for SeisSol, if it can import FLAG3D files.
Yeah, that depends which kind of format FLAG3D is writing out. So I don't know actually, but if you tell me which format that is, then.
Okay, then I would forward this to the Slack channel or one of the breaks. And
okay.
Thank you very much for the perfect presentations as usual. And if there are no further questions from the moment, I would say we have all a break until 11 o'clock. We'll bring up this by a slide, I hope so, and then continue with the next two codes. Yeah, and feel free to ask questions still in the Slack, that they will not get lost. Okay, so I hope everybody had a good break, got a bit of refreshment for the second part now. Did there come up any further questions to the talks before? We posted a few of the slides already in the Slack channel, and we will try to post the next slides there as well. So for all those who want to look up something. No further questions in the Slack. And I don't see further questions in the chat as well. So, okay. then
Yeah. Sorry. Can I?
Yes.
I raised a question in the chat. In fact,
Ah.
I'm not able to install Docker since my Mac is older now, older than 10.14 as indicated in the.
Yeah, are you in Slack? Then we can try to solve the issue in private conversation there.
Okay.
Yeah.
Thanks.
Okay. Good. So if anybody else has issues, just post in the general chat that you need help there or here in the chat. And we will try to solve this in Slack, so there you can easily copy commands and all the stuff. Okay, good. Then I would hand over to, I don't know who will present the SPECFEM3D stuff and Salvus, so, but I will stop sharing so you can start.
Okay, I will present SPECFEM3D. I need to share my screen. Oh, can you hear me? It's okay.
Yes, we can hear you perfectly.
Okay, perfect. Can you see my screen now? Or?
That's also fine.
Yes. Okay.
Ah, yeah. There are some scroll marks on the side, so maybe you can make full screen or. Yeah, but.
Like this, it's okay.
Text is still cut. Maybe just press Control P or something like this, or View and then
Control P.
Control Shift P. I don't know which editor this is, but yeah. I'll zoom a bit out because the method is cut away there, the title of the slide also.
Okay. Actually, I don't know.
View and then presentation. Yeah, perfect.
The presentation, I think it's. Do you see my first slide in full screen now or not?
It's showing a black screen.
A black screen. Oh, okay. Right. Okay. Not good. It is the same now.
Yes, it's the same, but yeah, maybe you can just close the navigation bar and then when you click on the contents on the left.
Okay.
Then you have a bit more space.
No, actually, I cannot.
Yeah. Click 2 times on contents and I think then it's gone. Yeah, perfect.
Okay.
Now we can see everything.
You can see.
So then, yeah.
Okay, it's not okay. Okay, so I will present the SPECFEM3D code. This is spectral finite element code to compute seismic wave propagation in 3D complex models. Initially, this code was designed to do global scale simulations at early 2000. It was developed by Dmitry Komatic. You can see here the kind of simulation he did at that time. It's, for example, the Sumatra 2004 earthquake. So this code computes all the waves, the body waves, the surface waves that propagate at the global scale. And the goal was to do precise simulation, more accurate simulation that was compared to the classical method used at that time. It was based on normal mode summation or 1D method in spherical symmetric curves. So this code takes into account the topography, bathymetry, ocean, and internal discontinuities and more complex physics like general anisotropy and attenuation. So this code was used initially to do this kind of simulation, and also it takes into account the shape of the Earth, the ellipticity of the Earth. It was not possible with method that was developed used at that time. So after this first application, the code was extended to regional scale simulations. The goal is to study the interaction between the waves and the geological structure at regional scale. The domain extends over a few tens, few hundreds of 2,000 kilometers. And this version of the code can be used, for example, for seismic hazard mitigation by computing shaking maps. We can see some movie of the free surface displacement. And to study the interaction between the different scenarios of earthquakes and the geological structure that are in the earth, like basin or mountain range, and to see if there are some region with potential damages or not. And then we are using SPECFEM now for other applications at smaller scales. Well, of course, on seismology at global and regional scale, but now we are beginning to use SPECFEM for ocean acoustics, and also in smaller scale for non-destructive testing. So I will show you 2 examples. For ocean acoustics, the challenge is about the frequency of the waves that propagate inside the water level. The attenuation in water is very low. That means we have a high frequency that propagates very far. So to handle this kind of simulation, we need to consider very big models with very small mesh sizes. That is a challenge for a computational point of view. Even in 2D, we need to use supercomputers to be able to handle this kind of simulations. And the second thing, it was to validate the SPECFEM method for this setup. So to do that, we did some experiment in water tank. In a lab, we are water tank. We did some records of ultrasound in this water tank, and we compare to the simulations. We had a good agreement, and that means the SPECFEM can be used for the this kind of simulation. You can see even with in the movie, even with a very simple model, a water layer in fluid in blue and solid in gray, just with 2 cement, you have a very strong complex wave field. So that means we need to use a very precise method that can handle all complexity of the bathymetry to be able to do a realistic simulation in ocean acoustics. So now the code is validated. We are beginning to use it for real size case in ocean and in Mediterranean Sea, for example. For non-destructive testing, the goal is to probe some materials. It has some application in industry to see if a building or if a bridge is not damaged. So the setup is the following. We have a transductor that triggers waves. It propagates inside the concrete, for example. And there are very complex interactions between the waves and all the scatter that are in the concrete. By studying the back propagated waves and compare to some simulations done by SPECFEM, we can tell something about the status of the material. Is it damaged or not, and take a decision if we need to fix the building, for example, or the bridge or not. So the SPECFEM is based on spectral element method. Initially, it was developed for computational fluid dynamics by Patera in 1984. And this method was extended by Computational Seismology and Capdeville to the seismic wave propagation. And there are at least two good properties of this method. It's based on the finite element method. That means we use mesh. With this mesh, we can mesh complex geological structures. We can precisely, and we also rely on very high degree polynomial interpolation inside each element. That is for the accuracy. So we have a flexibility of a finite element and the accuracy of the pseudospectral method, high polynomial degree interpolation. And one last thing is that this method is very efficient on parallel computers because we have no linear system to invert. We have a diagonal mass matrix in this method. So we deal with the equation of motions, the elastodynamic equations. So this one right here. It's just the density multiplied by the acceleration. It's equal to the force. There are 2 kinds of force: internal forces and source term. This represents the earthquake, an explosion, a load, something, an external source that triggers the waves. And here you have the divergence of the stress tensor. This is internal forces. And we solved this equation using the weak form. So the weak form is just multiplied by test function. Take the integral over the domain and do integration by part here of this term to make appear the surface term, which involves the traction. And it's interesting for seismological application to have this term here, because at the free surface of the Earth, the traction is 0. So we just need to remove this term, and we naturally handle the free surface condition in a very simple way. We can also consider attenuation using memory variable, an ocean load, or water level. So we have the two solutions. So the elements are ExaHydra. We have two kinds of elements that we can use in SpecFem. With ExaHydra with 8 control points, we just control the edge of the ExaHydra, or with 27 control points. That means we can bend the ExaHydra, the edge of the ExaHydra, in order to honor the structure, the different structure we want to mesh. It's more flexible to use this kind of element that linear element. Inside each element, we are using polynomial interpolation, Lagrange interpolation. Usually, we are using degree 4 to degree 7 interpolation. You have here an example of interpolation polynomials. Each polynomial is associated to one node inside the element. We are using the Gauss-Lobato-Legendre nodes. And these interpolation nodes are the same that we are using for quadrature rules for computing the integrals. And that leads us to have a strictly diagonal mass matrix. So we don't need to invert linear system. Thus, we use explicit time scheme. And this is very important for performance in a supercomputer. Since we are using ExaHydra or square in 2D, it's very easy to define interpolation polynomial in this kind of element, because we just define nodes in each edge of the ExaHydra and put the product of the polynomials, and that's straightforward to define interpolation polynomial in 3D, for example. So I just want to show you the mesh that was used initially in the first version of SpecFem Globe. This is an internal measure. It's an automatic measure for the Earth. You can see here a section of the mesh. You can note that at the surface there is small element, and the element increase with depth. There are two reasons for that. First, we want to precisely mesh the surface topography. And since the velocity of the wave increase with depth, we can increase the size of the element without losing the accuracy. So by optimizing this mesh, we can gain a lot of computational time without losing accuracy. So since we are using continuous Galerkin formulation, we need to use conforming mesh. So that means it's to go from one size of element to the second size of element to bigger size. We need to have some special brick. Here we are calling this doubling brick. We cannot do it for anyway. We need to have some special figure to handle the increase of size of the mesh. So this is done in internal measure. So to mesh more complex geometrical structure, we can use, of course, external measure. There is some example for a paper from Peter et al. In 2011. For example, to measure an asteroid, an external measure that trellis were used, or also for COBE. coffee milk, for example. At regional scale, we can use an internal measure here, for example, and for volcano, we have the choice. We can both use external measure or internal measure. It works for this kind of simple mesh. So if we want to go to more complex mesh, we need to use external measure like qubit 3D storage mesh. So once we have the mesh, when the mesh are very big, we need to use high-performance computing to solve the wave equation. Basically, a supercomputer can be seen as a lot of smaller computers that interconnect with the network. You can see a picture here. This was the first computer that they built to run SPECFEM globe initially. Actually, it's a desktop, that's a real desktop computer that are interconnect with the network. So if we have a lot of computers like this, we need to distribute the mesh, to split the mesh in small parts and to distribute in each computer. Each computer doing the computation in its part of mesh, and after communicate the solution to the other. So of course now we have the access of modern supercomputer like price resources. We need no more need to build our own computer in the lab. So to communicate between the two subdomains, we are using MPI, message passing interface. For example, here you have the domain decomposition. Each color is associated with one core, yes. And when the wave propagates from one side of the model to the other, when the wave reach the boundary of the model, to be able to compute the propagation in the other core, we need to communicate at the solution just at the boundary of the MPI slices. And we are doing this by an MPI communication in non-blocking way in order to optimize the code. And also we have an option to use hybrid MPI OpenMP parallelization. So, and this was done, this code was tested on a very big computer in 2016 in Japan. It's a K computer. At that time, it was the bigger computer in the world. So the simulation, it's at global scale. It was for 1.2 second period. This is a very big simulation because the mesh is about 10 billion elements. And to be able to do this simulation, they use the author use 80% of the K computer, around 82,000 nodes, and each node has eight core. They use 8 OpenMP thread for in each node. So, and to test the behavior of the code, they did some scalability test. So what we are calling strong scaling and weak scaling. The strong scaling consists to have a mesh and to split it in several MPI slices, and to increase the number of MPI slices and to see the speed up compared to the previous one. If we increase by a factor of 2 the MPI slices, we expect a speed up of 2. If it's the case that the behavior is good. So for this particular simulation, they did only two measurements because the mesh was too big to use a smaller number of nodes. After there was no more node to use bigger number of nodes. And the same for the weak scaling. The weak scaling, just we have a mesh. We increase the size of the mesh. In the same time, we increase the number of nodes, and we expect the same time to solution. So you can see in this figure the behavior of the SPECFEM on this computer is close to the ideal behavior. So that means the SPECFEM is very well optimized for this kind of computation. So, and also 10 years ago, the developer make a support for the GPU computing. The GPU is interesting because it's very fast. We can have a very good speed up compared to CPU. And this opens the door to the other kind of applications like seismic imaging, because in seismic imaging, we need a lot of simulation and fast simulation, not a big simulation, but a lot of simulation, and we need to have a time to solution very, very fast. So the way that they did, they rewrite part of the code in CUDA. It's a special language for the graphic card. And to be able to use also multi GPUs, the communication is also by MPI, like in CPU. And in this case, we need to pay carefully attention to the communication because it can be a bottleneck more than the CPU part. So we are doing a non-blocking communication and overlap some MPI communication by computation. And we can measure it in a test with we are calling a weak scaling. So this is published in 2010. It was the first paper published about the SPECFEM and GPU. So now the GPU are more performant. So at that time, the speed up compared to the CPU was around 10 or 20. But now we are speed up is about 50 or more, sometimes 100. So this the GPU is very efficient. The implementation of GPU is very efficient on SPECFEM. So that's why we are using now essentially the GPU computing. Since we have now access of very big GPU cluster in Europe, we have in Sinica Marconi 100 with have a lot of GPU, and we can do with this kind of hardware the agent tomography. The tomography, the goal is to image the subsurface, and the setup, for example, here in Southern California, is the following: we have a lot of earthquakes that occur that was selected in the region. The waves propagate from the earthquake to the surface that are recorded at the free surface by the stations. And the goal is to find a model that can explain the record at the surface. You can see here I think in black is the data, in red is the simulation in 1D model, the simulation in simple 3D model, and simulation in the final model. So that requires one simulation per earthquake, do a comparison between the synthetics and the data, perturb the model, redo a simulation, one simulation per earthquake. So for perturbing the model, we are using the gradient. So we need to do 3 simulations additionally. So for each iteration of the process, we have 3 simulations per earthquakes, and we need to do several iterations. So at the end, we need to do a few 10,000 of simulation to obtain an image like this of the subsurface. That's why we are relying on the GPU computing to have fast computation and to be able to do a lot of iteration to obtain a precise image of the subsurface. This is another example on Pyrenees. The setup is different because the earthquake are no more inside the box, but the earthquake at the teleseismic earthquake. These earthquakes occur far from the box, a few thousand kilometers. And we can use them for image exactly the same by comparing the synthetics and the data and find a model that can explain the data. We can image the subsurface. This is just below this line of receiver, and this is the geological interpretation. And also with SPECFEM Globe, the principle is the same. It's go to compare the data and the synthetics, and to use earthquake at the global scale and the global network. And you can see some model can be obtained by this adjoint tomography at the global scale. So SPECFEM is an open source package. You can find it in GitHub. This is an official repository. And it was developed from almost 20 years ago. And a lot of people were involved in development. And we are still developing it, optimize it. So we can you can see there are a lot of institutions like EPGP in France, Harvard, Caltech and Princeton in USA. So Barcelona Supercomputing Center, also NVIDIA did some development in SPECFEM. So you can find it in the GitHub. You can download it and install. You can find example of using it. So tomorrow we will see some basic configuration for SPECFEM and do some basic simulation. We'll learn how to do that. So thank you for attention.
So we have a bit of time for questions again. So no questions in the chat here, and also no questions in the Slack so far. Then thanks a lot for giving the insights on the code and the nice results.
Okay, I'm stop sharing.
So then let's go over to the next introduction to our last code, which is Salvus. Who's presenting?
Hello,
today?
I'll be giving the Salvus presentation.
Then the stage is yours.
1 minute here. Do you see, which screen do you see right now? The presentation?
Seems like a presentation. It's really colorful.
Yeah, that's true. All right, we got it. Yeah, so thanks everyone for being here, and I guess good morning, soon to be afternoon. My name is Michael Afanasiev, and I'll give the introduction to Salvus, which is the last code of the 4 that we'll be talking about over the next few days. And yeah, thanks to all the other presenters as well for such a cool introduction. So just a little bit of an outline of what we're going to talk about today before we get started. So I kind of want to give you first just an overview of, like, where we see Salvus kind of fits into the whole kind of computational seismology environment and the types of problems that it aims to solve. And then I'll go into a bit of detail on the different components to the package. And there's kind of 5 main parts of Salvus, and I'll do a little deep dive into each of those to get some more information. Then I want to go over a few applications that primarily some students and other researchers have been working on using Salvus to solve problems in their own studies. And then finally, just an introduction to what Mondaic actually is and kind of how it came about. Of course, it might be a name that not everyone is familiar with. And then finally, just a quick teaser of what we're going to do on Thursday in the actual tutorial. Okay, so kind of a quick overview of Salvus. Like the other codes that we've heard about today, or like one of the main applications of many of them, Salvus is primarily a code for wave propagation. And to get started, I just want to give an overview of the types of applications that Salvus is generally used for. So its original purpose was essentially to have a consistent interface for simulation and inversion across different geological domains. And this kind of goal was inspired by the collaborative seismic Earth model project in the Seismology and Wave Physics group at ETH. And I'll explain that a bit more in a few slides. But essentially, we were looking for an easy way to switch between running simulations on a global scale, like or planetary scale. For instance, you can see an animation of Mars here, but also kind of take the techniques that we were developing, the imaging and modeling techniques that we were developing on the global scale, and then also easily apply them to different scales as well. For instance, on the right here, you see a regional scale simulation for a subsea distributed acoustic sensing survey array. So at the time when we began, there wasn't really an option to kind of switch through all these scales easily. So we decided to start from scratch and write a solver that would allow us to do this. And kind of in that process, this really required a lot of flexibility in the methods that we implemented. And this requirement of flexibility really opened up a lot of doors. So in order to make the kind of domain independence work, we really had to make sure that not just 3D domains were accessible, but also 2D domains as well. For instance, in exploration geophysics, the character of certain surveys really requires or greatly benefits from a 2D simulation and a 2D inversion. And 2D methods are just generally still widely used for their efficiency and kind of as a low-cost alternative modeling method for the rapid development of new full waveform inversion algorithms, for instance. So this led to some interesting work on the exploration scale and in higher frequency applications such as borehole acoustic modeling as well. And this was an application we really didn't have much experience with before the interest arose. And this is where we're really trying to look at the character of how borehole interface waves or Schulte waves interact with small fractures in the borehole to try and ensure that the boreholes remain, the integrity is still there after time, and just to do near borehole imaging. And then finally, as Vadim got up, as Vadim mentioned, the kind of almost the next frontier of full waveform inversion applications is in the more ultrasonic or medical imaging and non-destructive testing frontiers. So this is something that's been relatively underexplored, with the primary domain of waveform inversion being in seismology and specifically exploration geophysics. But we've really started moving as well recently into the ultrasonic scale, so kind of upping the frequency, reducing the spatial scale, and applying full waveform inversion to techniques like transcranial ultrasound and into non-destructive testing for corrosion and damage detection. So I hope this kind of gives you an overview of the types of problems that we tried to solve within one package with one consistent interface. So in the end, Salvus is a code for multi-scale full waveform modeling and inversion. And we're really trying to bring all applications which can be studied by waves together under a consistent and easy to use interface. So to summarize, Salvus supports 2 and 3D visco, acoustic and elastic physics, including full anisotropy in the elastic case in 2 and 3D. It includes proper modeling of the fluid solid condition in coupled domains as well. And through a custom built meshing toolbox, we support unstructured domains of graded complexity. So for instance, if you think of a Cartesian domain, just a homogeneous box with no specific geometrical quirks, you can get some efficiency gains by realizing that all the elements are the same size and there's some terms that might not need to be computed on the fly. But also, of course, when we look at the globe, when we look at topography, going to a fully unstructured mesh is just necessary to resolve the realistic geometric complexity that we have in some of the applications. And then finally, of course, also as Vadim mentioned, these problems can get expensive. So Salvus does run on your laptop, also onto high performance computing hardware, which we'll see during the course of this workshop, along with the other codes. And then finally, into cloud-based infrastructure as well. And I guess altogether, I could sum this up as, yeah, Salvus is a high performance software package really tailored for applications, for applied waveform modeling and full waveform inversion. Of course, focusing on the traditional performance, reproducibility, and ease of use. But I guess we really try to make it as easy as possible to get simulations and versions up and running, usually with just a few lines in a Jupyter notebook on some realistic domains, and try not to sacrifice the performance that is, of course, really necessary for getting these problems to run at scale. So I hope that's a nice kind of overview of really what we're focusing on these days. And over the next few slides, I want to give kind of a breakdown of the individual components of Salvus and how it really all works together as one comprehensive package. So on the whole, Salvus is broken down into what we call 5 main packages. That's Salvus Compute, Mesh, Flow, Opt, and Project. Now, some of these might be pretty self-explanatory from their names. I mean, of course, Compute is the compute engine. Some might be less self-explanatory, like Salvus Project. So I'll go into them one by one and show you some examples of the individual areas that they target. So, like I said before, the whole kind of philosophy behind the Salvus Project and Salvus Compute in particular was inspired by the Collaborative Seismic Earth Model project at ETH. And the goal here is essentially to approach full waveform inversion on the global scale in a multi-scale way, to have low frequency, long wavelength updates on the continental scale, and then high frequency subregions. Well, high frequency meaning tens of seconds, but higher than, let's say, 50, 60 seconds on the global scale, to really get the resolution higher where we have the data to do it. And so to accomplish this, we really picked up and ran with the spectral element method, which has been present in our community for 2 decades or longer, really popularized by Dimitri Komatic and further developed by Daniel Peter, Jeroen Tromp, Max Friedman, Emmanuel Chaljoub, Jan Kaptevel, and many others, kind of really pushing the theory and implementations forward here. And of course, really applied to some cutting edge use cases by Ebru Bozdag and Carl Tape, showing how adjoint tomography and the spectral element method can really add value at both regional and global scales. So in terms of a numerical method, Vadim gave a great overview of that, and I won't really get into details there because there's some other stuff to talk about as well. But just to confirm, so Salvus is based on an arbitrary ordered continuous Galerkin spectral element solver, which, as I mentioned before, runs in 2 and 3 dimensions, and which solves a trivial multi-physics problem because there's still multiple wave equations we're solving. It's not like we're coupling to a fluid flow equation, but we do actually handle the coupling condition along fluid and solid interfaces, as well as along the free surface via the traction-free condition. In terms of performance, so the kind of numerical and discretization backbone of Salvus really relies on PETSI, and specifically the DMPlex package. And what this is a kind of way to look at an unstructured mesh as a special type of graph called a Hass diagram. And this really allows us to be, almost infinitely flexible in the topology of the mesh that we actually solve. And what's nice about this is that it allows for a runtime mesh decomposition. So we don't need to kind of perform a, independent partitioning stage. All this happens at runtime on the fly and very efficiently. And because of this, Salvus is able to scale from laptops to supercomputers. And really just to say, so the DMPlex package in PETSI is primarily the work of Matt Nepoli at the University at Buffalo, and a colleague of ours at ETH, Zurich, Václav Hapla, recently implemented a fully parallel mesh reading layer to that, which has been instrumental in running some of the bigger simulations that people have been interested in. But so of course, once the mesh is decomposed, we also have good scaling to the time loop. You can kind of just see some graphs over here from Václav's newest paper. And of course, need to take into account the asynchronous communication, especially on GPUs. And in terms of programming languages, Salvus Compute is really the kind of the compute core, and it's written in modern C++ and CUDA for GPUs. with further extensions under work right now. So Salvus can be really kind of is the high performance background base that runs the simulations and performs the adjoint computations to get gradients available for full waveform inversion applications or other modeling applications. Now, as you know, there's been a few talks here, and I think everyone's already brought up meshing. This is just always an issue for some type of method that requires a discrete and especially continuous mesh or conforming mesh in our case. So in order to tackle this problem and to really deal with what we saw were pretty big limitations in the application of engineering packages like Trellis or Qubit to geological applications in particular, was to introduce Salvus mesh. So this is kind of an in-house meshing toolbox, which is specifically built for geological applications. What I mean by this is that we take into account things like the variation in velocity with depth, and also have integrations with various topographic data services like the GMRT database or the Appears databases, where one can kind of download topography for a certain geographical region, filter that topography so it's not too quickly or too slowly varying for the frequency band, and then generate a mesh from that from just a few commands. And what's also kind of been pretty neat and quite important is this whole kind of focus on local and automatic mesh refinement techniques. So what you're looking at on the screen right now is a classical example that you might have in exploration geophysics, where we have an oceanic layer on top. So that's the blue elements that are relatively big. And then we have an extremely slow velocity sediment layer just below the seabed. Now, of course, usually if we want a conforming mesh and we want to ensure that we maintain the advantages of explicit time stepping, we would either need to set perhaps the entire mesh to the resolution that's present or to the wavelengths that are present in the slow velocity layer, or we can go ahead and just do local refinements to basically not overly do a computational overkill on the entire domain by meshing everything in such a fine size. So yeah, there's some conforming and automatic refinements capabilities that are built in that can kind of detect where the velocities are too low, and then add some nice little refinements there, so we can keep computationally efficient even with very low velocity regions. Something that's also been pretty exciting and is something that I'll expand on in the application slide in a few, is this whole idea of kind of target-oriented mesh design. So we kind of want to say that this idea of exploiting directional complexities in the wave field and smoothness in certain directions is really built on the work of Tarje Nielsen-Meyer and Quangai Lang with their AxiStem and AxiStem3D package. So we have a similar approach to kind of take to speed up simulations in the presence of certain types of characters of the wave field, such as azimuthal smoothness. And this allows us to run pretty high simulations at a lower cost than you would have in a fully 3D method. And we'll show some advantages of that later. And then finally, I kind of just want to show how this all works, because the user interface of a meshing package, I think, is the source of many people's nightmares. It certainly was mine in the early years of my PhD. So really, in the end, this is kind of a Python package as opposed to the high performance C++ core that really just exposes a pretty simple interface that allows you to download topography and select your frequency and velocity model and automatically mesh a region based on that information. And this is kind of just back to the what was originally present on one of the intro slides. So this is the DAS example I showed before, and there's quite a bit of complexity here. We do have an ocean. So this is off the coast of Monterey Bay. We have an ocean, and you can see a little shoreline there and a coupled fluid solid simulation running through both of them. And in the end, this is just a few commands in a Python notebook to get this whole mesh set up and running. So yeah, if you're interested, that's also a tutorial on the website that you can check out. All right, so that's kind of the compute backend and the way we actually generate our domains. The next thing that we really worked on in Salvus is something we call Salvus Flow. And what this really tries to do is kind of abstract away the compute resources. So what the problem this aims to solve is the need to kind of log in and manually shepherd jobs on different HPC systems, maybe on your laptop, maybe in the cloud, and kind of just all the back-end work of interacting with the queuing system and all of that stuff happens within Salvus itself. And so the user can really just switch compute sets on the fly, do a small simulation on your laptop, and then scale up to a supercomputer to go to the 3D case. And so Salvus Flow is kind of this machine abstraction layer. And it's really in the end how the user actually interacts with Salvus. Now, like the meshing toolbox, this also has a Python interface. And we generally run these things through Jupyter notebooks, but of course you can also run them in a bash or a Python script if you'd like. But Salvus Flow gives you kind of nice visualization tools. We can look at meshes just in the notebook itself. We can see where sources and receivers lie. Maybe you can see it on the little picture there, this red line and the purple dots. I'm not sure how well that translates, but it kind of just gives you a nice, easy QC step before you run simulations to make sure that everything makes a bit of sense before you get going. And the way that we define sources and receivers are all Python objects which are validated at creation time. So you have a hard time making something which makes no sense. And as an example of that, many times kind of previously, I would definitely have this issue that I'd make some sort of typo in an input file. Then I'd be waiting in the queue for an hour or so on an HPC system and then realize I spelled strain and I forgot the I. So kind of stuff like this, we really try and catch it at an early stage. So, Salvus won't let you submit this job if you go through the Salvus Flow interface. Kind of tells you, okay, there's a typo in your input file. Here's where it is. Please fix that and then try again. And then kind of along with all that, there's a nice little features of kind of monitoring the progress of ongoing simulations, seeing where they are in the time loop, for instance, and also automatic uploading and downloading of all your input files and your mesh files. So really all you do is kind of, you sit on your local computer and click run and all that stuff will happen in the background, which is pretty cool. And then, yeah, finally, this is really the compute abstraction layer. So you can kind of see here what we call a site. And this is just a little machine we have in the office called Tiny. This is just kind of you set this up once in the Salvus kind of configuration file, and then that's available as a site to use, and all this uploading, downloading will happen automatically in the back. So yeah, we'll definitely see some of Salvus Flow on Thursday, because this is really mostly what the user does see. All right, so now on to full waveform inversion. Of course, the goal of kind of developing this whole package in the first place was for the ability to do waveform inversion on different scales. And to tackle this, we basically built a nonlinear inversion framework, which is really tailored to full waveform inversion applications itself, with some kind of special features that'll go into right now. So the goal here, of course, was as before, we want to apply full waveform inversion techniques on let's say a pipeline or some deformed domain, which might be relevant for non-destructive testing, but we're still global seismologists, so we want to use the same techniques on regional to global scale waveform inversion. And so to do this, we implemented features like regularization on unstructured grids via the implementation of a diffusion equation. And this is really nice because what it allows us to do is kind of add directional and wavelength dependent smoothing to different areas in our model. And what this would do is, for instance, at depth, where we know our wavelengths are longer and therefore we get less resolution, we can automatically smooth more at those depths than we would say at shallow depths where we have higher frequency waves and a higher resolution criterion. And of course, just in general, this helps us do regularization on fully unstructured domains. Because you can imagine applying something like a normal kind of Cartesian Gaussian smoother on any one of the domains on the screen right now. This just won't work out very well, because what do you do at the boundary? So yeah, we'll also get into detail on this on Thursday, but it's a pretty neat feature. In terms of the actual inverse methods themselves, we've kind of focused on truss region Newton type methods. And the nice thing here is that once the inversion gets going, we kind of internally build a model of what the local minimum looks like around our current place in model space. What this allows us to do is get rid of the step length search simulation after a few kind of primary iterations. So this actually saves quite a bit of time. If you think of 50 to 100 iteration inversions, we don't need to run those extra simulations to kind of find out the minimum of the local region. We can just take the quadratic approximation that we build through the trust region approach and automatically determine the step length. And then finally, what we really try to do here is kind of give a lot of feedback on how the inversion is progressing. I mean, these are big problems usually, and they're in 3D, and understanding what's going on with the inversion is an issue. So what we try and do, and we're still kind of working on this, but come up with nice metrics to present to show how the actual inversion is proceeding. And we'll go through in detail on Thursday, what these graphs actually mean. But as a spoiler, the one you're seeing is a good sign. What this means is that our quadratic approximation here in purple is very close to our actual reduction of misfit that we're getting via the inversion in green. And when those two things are close together, we know that, okay, we're doing something right and the inversion is going in a nice direction. All right, so finally I get to maybe the less trivially, you can't really understand what it is from the title type thing. And this is Salvus project. So the goal here was to do multi-scale waveform inversion. And to kind of support this, we got 4 packages that kind of take up different parts of the workflow. But to be honest, by the time all that stuff was kind of developed, we'd actually gotten a bit stuck. We were happy with the solver performance and the kind of Pythonic interface to actually interacting with the stuff and the general user interface. But we really realized that kind of one of our most desired modes of operation wasn't yet possible. And this was the idea that, at the end of the day, it should be possible to shut down your notebook or computer, go home and go to have a sleep without worry about, losing where you were, or about your process crashing or your computer just shutting off because someone unplugged it. And then basically losing data from that process. So this is really the kind of domain of Salvus project. And I'll show how it works in the next slide. And of course, we want this to again work across 2 and 3 dimensions and across different types of domains. And this becomes especially important when we're talking about kind of long-running full waveform inversions, which might last a few days to a week or something like this, where we just kind of need some intermediate way to save state and to be fault tolerant. And we do this by essentially keeping a serialized and state-aware database on your local machine. What does this mean? Well, when we set up a simulation on Thursday, we'll see that these simulations are composed of several independent components. We, for instance, have a background model, a volumetric model, and maybe a model of topography. And the way we keep track of all this is by essentially hashing each type of input, and that's given a unique hash value. And when we create data from a realization of these different inputs, we get a set of synthetic data or waveforms, which itself is given a hash value, which is a combination of the previous hash values. Now, the interesting thing here is that, okay, this sounds like a lot of data. We kind of keep everything, and that's true. But of course, if we run out of space or if we want to delete something, we can actually just keep the hash. This is just a small text representation of what we actually computed. And that hash is information and that connects it to all the input files that created that certain type of data. So we're able to go back later, if I deleted some synthetics from iteration 1 because I ran out of space, I can easily compute those again because Salvus project knows all the intermediate steps that were required to recreate that data. What this really allows us to do is kind of, first of all, save on computations, because we know that if something has been computed or not by the presence of a hash. And if it has been, instead of recomputing seismograms, we kind of just serve them up from where they were. But also this allows us to kind of statefully share projects and models with colleagues without worrying that every single step of the workflow is there. So for instance, this has a nice interaction with the IRIS Earth model catalog and different stuff that we can just look at. And essentially this all happens kind of with as much or little attention as you like. And you can, this is a open source database of how the current simulation and project is looking. And everything is stored in a nice directory structure that you can kind of go through and peruse at your own leisure if you like as well. And right, all this kind of stuff is now the way that we really like to interface with Salvus. And in addition to the tutorial we'll do on Thursday, there's a lot of stuff online that shows it in action. All right, so now I just quickly want to go through some cool case studies that I just want to highlight, some stuff that I've found particularly interesting over the past few years. So for instance, Jorge Castellanos of Caltech, recently just graduated, had a really cool project going on where he kind of used a lot of the features I'm just talking about to really model the reverberations of ocean waves on a transoceanic, not quite a DAS cable, but a fiber optic cable with some really interesting results. I want to highlight the work of Dirk Philip van Heerwaarden, who's kind of been using Salvus as an engine to build his own mini batch or randomized inversion methodology that drastically reduces the number of simulations required to actually get a coherent waveform inversion. Also Sylvie Thrasterson, who's got a new paper coming out very soon that goes into much more of the details here. And there's actually an updated model, which you'll need to check the paper out to see, but it looks quite beautiful. So essentially Sylvie starting from a 1D background model and combined with DP's work as well, you saw on the previous slide, is really starting and getting a high resolution picture of the Earth on the global scale at long frequency rates, using some of the data adaptive meshes that I spoke about before to make things a lot faster. Laura Koppen at Utrecht, this is a cool project investigating the forward and back scattering of body waves on mantle plumes. Quite big simulations, also requires the data adaptive mesh techniques that I was talking about before. And then finally, on the medical imaging scale, I just want to highlight work by Patrick Marty, who's been applying Salvus to transcranial ultrasound tomography for early cancer detection and really investigating the effect that the skull has on how we can resolve the interior of the brain. So I just want to kind of follow up by just kind of explaining what Mondaic is in case any of you don't know. So Mondaic is actually a spin-off that myself and the other Salvus developers started near the end of our time at ETH. And essentially what the mandate of this company is to kind of, ensure the long-term maintenance and growth of Salvus for applications in industry and in academia, and to kind of, try and kind of provide a really quick way to get to the application and to perform some kind of applied science on different domains. Of course, this comes with a lot of back-end work on making sure the code is robust and tested, and with a long continuous integration pipeline, and basically just also a lot of support that we provide everyone who's using it. And I guess, yeah, we are a company and this is now our full-time job. So we do usually ask for a license fee, but in general, we're extremely flexible about this. If you're interested in Salvus and using it for one of your problems, just give us a shout, and we've always worked something out. So we'd be happy to hear from you if you're interested here. And then finally, we are growing and have some successful applications across many scales with many different, I'd say, clients and partners. And yeah, so it's been an interesting journey so far. And I hope that you find the tutorial stuff very educational and interesting as well on Thursday. And speaking about Thursday, what will we do? So we will do a continental scale full waveform inversion from scratch using real data. And we'll focus on the European region. Now, just due to the fact that we're all sharing, one big supercomputer, we won't be able to do anything at super high frequencies or anything like that. But you really, I think we'll get a feel for the different steps involved in doing a full waveform inversion, from data processing to kind of, event selection and quality control. And, if that might apply to the use in Salvus or any other package as you go forward. But I hope that it gives you kind of an overview of what's practically involved in such an application. So here are your instructors. It'll be myself as well as Christian Boom and Leon Krischer. If you're not aware, they're all very excited to show you guys how this all works on Thursday. So yeah, that's it. Thanks for listening, and yeah, happy to take any questions now. But of course, we'll also be here all week.
Thanks a lot for this talk. And see, no questions in the Slack.
All right.
But I guess there will be a lot more, during the tutorial then also, or yeah, depending on when people look at the slides the second time when you upload them to the Slack. Maybe.
Sounds good.
Give them maybe a minute more time.
And also just feel to reach out on the Slack or anything. If you'd like anything explained again, we'll be monitoring that, of course.
Okay, then if there are no questions for the moment, I would say we have a lunch break until we start with the lightning talks, where we get to know you as a participant. And let's do the lunch break until 1:15.
Yes.
Let me put up a slide.